Hydrocarbons are classified as alkanes, alkenes, and alkynes. Consider ethane, ethene, and ethyne as their respective examples. The ethane molecule is ditetrahedral and has a bond angle of 109 degrees 28 minutes. Ethene is a planar molecule with a bond angle of 120 degrees, while ethyne is a linear molecule with a bond angle of 180 degrees. All these three hydrocarbons differ from each other in geometry and bond angle due to a difference in the state of hybridization of carbon atom in them. In this topic, we will study the sp3 hybridization of carbon in alkanes and how it is responsible for its tetrahedral geometry. We will explain it by taking ethane again as an example. There are 2 carbon atoms and 6 hydrogen atoms joined by single bonds in this molecule. The orbital picture of ethane looks like this. We can thus visualize 7 internuclear axes between them. A chemical bond formed by orbital overlap along the internuclear axis is a sigma bond. Thus, both the carbon atoms are surrounded by 3 carbon-hydrogen sigma bonds and 1 carbon-carbon sigma bond. These bonds are directed along the corners of a regular tetrahedron, and all carbon-hydrogen bonds are of the same bond length. Let us now remove the 6 hydrogen atoms from this structure. Also, drag the 2 carbon atoms apart. We can clearly see 4 equivalent sp3 hybrid orbitals around each carbon atom. Each of these orbitals has one lobe bigger than the other and is occupied by a single unpaired electron. Now, consider a carbon atom having atomic number 6 in the ground state. Its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. On excitation, an electron jumps from the 2s orbital to the 2pz orbital, resulting in an electronic configuration of 1s2, 2s1, 2px1, 2py1, 2pz1. In order to form 4 sigma bonds with other atoms, the 2s, 2px, 2py, and 2pz orbitals of this atom intermix. This process of intermixing of atomic orbitals is called hybridization. As a result, 4 equivalent orbitals called sp3 hybrid orbitals directed along the 4 corners of a regular tetrahedron are formed. When 2 such sp3 hybridized carbon atoms approach each other along the internuclear axis and overlap, a carbon-carbon sigma bond is formed. This bond has a bond length of 1.54 angstrom. 6 hydrogen atoms now approach and overlap the remaining 6 sp3 hybrid orbitals of both the carbon atoms, forming sigma bonds with bond length of 1.09 angstrom. In other words, whenever a carbon atom in an organic compound forms 4 sigma bonds which are directed along the corners of a regular tetrahedron, it is sp3 hybridized. Besides sp3 hybridization, the excited carbon atom may also undergo sp2 or sp hybridization. During the formation of a double bond, 1 2s and 2 of the 2p orbitals hybridize. Consequently, this hybridization is termed as sp2 hybridization. The hybridization leads to the formation of 3 equi-energic sp2 hybrid orbitals. As you can see, each sp2 hybrid orbital is bilobed, one lobe bigger than the other. The half-filled p orbital, which was not involved in hybridization, lies at right angles to the plane of the equilateral triangle. Now, let us understand how this hybridized state results in the formation of a double bond. For this, imagine a similar sp2 hybridized carbon atom approaching this carbon atom. As these atoms come closer, an orbital overlap takes place along the internuclear axis. This bond is called a sigma bond. At this stage, the unhybridized p orbitals, which lie above and below the plane of the sigma bond, also come very close to each other and overlap laterally, resulting in the formation of a pi bond between the two carbon atoms. Thus, there exists one sigma and one pi bond between the two carbon atoms. The other two valencies of each of the carbon atoms are satisfied by 4 1s orbitals of hydrogen, hence forming an ethene molecule. Another process of intermixing, called sp hybridization, results in the formation of two sp hybrid orbitals. Now, this carbon atom is ready to combine with other atoms. Imagine another sp hybridized carbon atom approaching this carbon atom, such that the sp hybrid orbitals of the two carbon atoms face each other. These orbitals overlap along the internuclear axis, resulting in a sigma bond. Each of the carbon atoms also has two unhybridized p orbitals, namely the py and pz orbitals. These orbitals, which lie above and below the plane of sigma bond, also come very close to each other and overlap laterally, resulting in the formation of two pi bonds between the two carbon atoms. The fourth valency of each of the carbon atoms is satisfied by two 1s orbitals of hydrogen, which also make sigma bonds along the internuclear axis. The quest of the carbon atom is now complete, and an acetylene molecule is formed. To summarize, we've studied that whenever a carbon atom in an organic compound forms 4 sigma bonds directed along the corners of a regular tetrahedron, it is sp3 hybridized. A carbon atom that forms 3 sigma and a pi bond is sp2 hybridized, while the one in which it forms 2 sigma and 2 pi bonds is sp hybridized.